Hello students, welcome back to another video. Today we're going to be focusing on speed and velocity. You can't really talk about motion without mentioning speed and velocity. These are both terms that we use to describe how fast something is going, but there are some differences between speed and velocity. So we're going to go over those differences today, and then I'll provide an equation for each term and then apply that to an example. Okay, starting with speed. Speed is a scalar measurement of how fast something is going. Okay, and if you don't remember what a scalar is, scalars are variables that do not care about direction. Okay, here I've written that out just to emphasize that a scalar does not care about direction. Kind of like how distance doesn't care about direction. Okay, we're going to come back to that. But now let's compare that to velocity, which is a vector. Vectors are variables that do care about direction. A vector that we've already learned about is displacement. Okay, so in summary, speed is a scalar variable, kind of like distance, and those variables don't care about direction. Whereas velocity is a vector variable similar to displacement. Because of these differences, we have to calculate speed and velocity differently. So now I'm going to show you the equations that we use for each of these. To calculate the average speed of some objects, we use this equation, which says that the average speed is equal to the distance traveled divided by time. Instead of writing this equation just with words, I'm going to shorten this equation to just use letters that represent each of those variables. Okay, here's my new equation. The S here just stands for speed. The D stands for the total distance traveled. And on the bottom here, I have a little triangle, and that symbol is called a delta. And all this represents is that whatever variable comes after it is changing. So I have delta t, because over the course of something's motion, time changes constantly as that thing moves. Next, let's look at an equation for average velocity. I've written that out here, and it says that average velocity is equal to displacement divided by time. Once again, I'm going to condense this equation to just a letter form. Here I have v for velocity is equal to delta d, which is the change in an object's position. Right? Displacement is how far something ends up from where it started, which in math terms is its final position minus its initial position. Okay, I've written this out here in this other form, where instead of writing delta d, I write the final position minus the initial position divided by the change in time is equal to the velocity. Both these equations are true. This one's just a little bit more specific, but this one, if you can recognize that the delta d is displacement and not distance, then you're going to be fine. Okay, now I have different equations for my average speed and my average velocity as well. So now I'm going to apply this to an example. Okay, let's say I have some student walking through the hallway, and he walks forward 10 meters in 10 seconds. So he moves forward that distance in that amount of time, he stops in place and then checks his pockets for 3 seconds and realizes that he doesn't have his phone. Then he turns around and sees that his phone was dropped halfway through his path, so he quickly goes and picks it up. Okay, so he quickly goes backwards 5 meters, and let's say it takes him 3 seconds to go back there. Okay, so in total, he went forward 10 meters in 10 seconds, stood still for 3 seconds, then turned around and came back the other direction 5 meters in 3 seconds. Okay, I'm going to transfer this information into a position versus time graph really quick. Here's my graph for that same example. You can see that for the first 10 seconds, the student was moving in the positive direction until he got to the 10 meter mark. Then he stood in that place for 3 seconds, or from 10 to 13 seconds. And then from 13 to 16 seconds, he had turned around and went the opposite direction until he got to the 5 meter position line. And I'm going to erase what's on top just to have extra room. And next we're going to analyze what's going on here, and we're going to do some calculations of speed and velocity. The first two questions I want to ask are, what was the total distance traveled and what was the displacement? Okay, distance I'm going to represent with just a d, and displacement I'm going to represent with a delta d. Okay, for distance I know it's just the total distance traveled, so I'm just going to add up how far that student had moved. I know he moved 10 meters forward and then 5 meters backward, so I just add those two numbers. Okay, 10 meters plus 5 meters, of course, is 15 meters. And now we're going to calculate displacement, which is how far the student ended up from where he started. I'm going to use the equation I used previously, which says that displacement is equal to the final position minus the initial position. Okay, my final position is equal to 5 meters. Okay, when I do 15 divided by 16 in the calculator, I get 0.9375. I'm just going to round that to 0.94. Okay, so my average speed here is 0.94 meters per second. And next I'm going to do the calculation for average velocity. Okay, my equation for average velocity is displacement divided by the change in time, and my displacement was 5 meters in the positive direction. Alright, my change in time is still the same as it was previously. This is from 0 to 16 seconds, so 16 seconds. Alright, when I put this in my calculator, I get 0.3125, and I'm just going to round that to 0.31. Alright, so my average velocity is 0.31 meters per second in the positive direction. Okay, and the direction here is implied from it being a positive velocity. If I had put a negative here, I would know that he was moving in the opposite direction. Alright, now you might be wondering, what about the slope? Don't you need slope to calculate velocity? And that's what I'm going to touch on next. Using the slope on a position versus time graph is how you can find something called the instantaneous velocity. These two things are the averages. This is the average speed, and this is the average velocity. These are both measurements that consider the entire duration of the motion. Whereas if I just check the slope of this little line here, then I'm finding the velocity or the speed in that exact moment of time. So looking at this first segment, I see that the student went 10 meters forward in 10 seconds. So if I do my slope equation there to find the velocity, I'm going to do rise over run between any 2 points on that line. I like to just do the beginning and the end. So starting here, I rise from the 0 to the 10, and then I run from the 0 to the 10 as well, in the x direction. So I'm going to plug those in to rise over run, and I get 10 meters divided by 10 seconds. That's just 1 meter per second in this time. I went ahead and wrote average AVG under this and also this, just to be more specific, that these equations are for the average velocity and the average speed. Okay, of course during this time, whenever he's not moving, his velocity is going to be 0. And that's evident in the graph because there's no slope. And I know I'm getting a little crowded here, but just to finish off the example, I'm going to calculate the instantaneous velocity during that last segment as well. Okay, if I do my rise over run, I see that it rises from 10 to 5. Okay, so since it goes down from 10 to 5, I'm going to say the rise is negative 5 meters. And then the run goes from 13 to 16 seconds, so it's 3 seconds. Alright, so my instantaneous velocity in that last section is negative 5 meters divided by 3 seconds, which I'm going to round up to negative 1.7 meters per second. Okay, I'm sorry there was a lot going on there in that example, but just to break it down one more time, the average speed of something's motion is the total distance divided by the change in time. The average velocity is the displacement divided by the total time. And those two things are different than instantaneous velocity, which you find with the slope. I know that the instantaneous velocity in the first section was 1 meter per second. Whenever he was standing still, it's 0 meters per second because he's not moving. And then in the last section, it was negative 1.7 meters per second. All of that is calculated with slope, whereas those other averages are calculated with those equations that I showed you earlier. Okay, that's going to be all for today's video. Thank you guys. See you next time.